If you walk onto a factory floor tomorrow, right, and you see this massive, I mean, like a $10 million machine just sitting there,
Yeah.
completely idle, for 2 hours, you probably look at that and think, well, that's just a mechanical limitation.
Right. You think it's just the cost of doing business.
Exactly. But you aren't looking at a mechanical limitation at all. You're actually looking at this massive optical illusion. And it's an illusion that is secretly, quietly bankrupting the company.
It really is.
So welcome to today's deep dive. We're looking at a concept that, honestly, it fundamentally changes how you view time and efficiency and capacity.
Yeah, whether you're, managing a sprawling manufacturing plant or
A software team, right?
totally, or even just trying to organize your own workday. It's a pervasive blind spot.
It really is. So for you listening, we're pulling from a really fascinating stack of sources today to unpack this. We've got structural analyses from Prasad Ban.
Right, the operations analyst.
Yeah, he's brilliant. He bridges that gap between physical hardware realities and high-level strategy. And we're pairing his work with methodology from the Center for Lean Excellence.
Plus some really hardcore mechanical breakdowns from lean production.
Exactly. And the core mission for you today is to understand this revolutionary, completely zero-cost mindset shift. It's known as hidden changeover inertia.
Hidden changeover inertia, it's such a great term.
It is. Okay, let's unpack this. It all hinges on separating what we call internal versus external tasks. But to really put the scale of this waste into perspective, we have to look at how different environments handle transitions.
Yeah, I love the analogy the sources use here. Think about if you or I get a flat tire on the highway.
Oh man, a total nightmare.
Right. It is a whole ordeal. You pull over on the shoulder, cars are flying by.
Yeah.
You spend like 5 minutes just remembering where the jack is in your trunk.
Under all the groceries and junk.
Exactly. And you're sweating on the side of the road, cranking this heavy car up, fighting with a rusted lug wrench. You're getting grease literally everywhere.
Best case scenario, what? It takes 15 to 20 minutes?
Yeah, 15 minutes if you're lucky and nothing goes wrong, just to get back on the road.
I am already stressed just thinking about it, honestly.
But then you compare that everyday reality to a NASCAR pit crew.
Right.
A car pulls off the track, 4 tires are completely swapped out, the gas tank is filled, the windshield is wiped clean.
The driver gets a drink of water.
Yes. And that car is roaring back out onto the asphalt.
Mm-hmm.
And that entire sequence takes less than 15 seconds.
Less than 15 seconds. It's wild. You're taking a 15-minute ordeal and compressing it into a fraction of a minute.
But the analytical goldmine in that comparison, and this is where we really start our dive, it isn't about human speed.
Right. They aren't superheroes.
No, exactly. The 14-minute and 45-second difference doesn't exist because NASCAR mechanics are like radioactive mutants who move at the speed of sound.
Though it looks like it.
It does look like it. But the speed is actually an emergent property of this militant, rigorous separation of tasks. They do absolutely everything physically possible before the car ever comes to a halt.
Right. If you watch a pit crew, the tires are already out of the warming blankets. They're perfectly positioned on the ground.
Exactly. The mechanics are holding the pneumatic drills.
Yeah.
And the drills are already spinning.
Yes. They are literally leaning over the painted line, just waiting for the asset to arrive.
They've separated the preparation from the stoppage. And that brings us to the core thesis of our discussion today. What happens to a company's time, its capital, and, its raw productive capacity when it fails to make this separation?
Which is the hidden cost.
Yes. The financial and operational hemorrhage that occurs when you don't do the setup before the process stops is just staggering.
And that is really our focus today, exposing those hidden costs of ignoring task separation. But I mean, before we can fix it, we have to understand why smart people let this happen in the first place.
Right.
The sources refer to this as the paradigm blind spot.
It's basically the lie we tell ourselves about how systems work.
Yeah, so in the manufacturing world, and again, if you're listening as a knowledge worker, just map this to your own software deployments or whatever. Plants implicitly assume that a multi-hour changeover is an inherent mechanical property of the equipment itself.
Right. They look at a massive stamping press and say, well, this machine just takes 2 hours to switch over to a new product line.
It becomes this self-fulfilling prophecy, right?
Totally. Because they believe the machine requires 2 hours of downtime, they never actually investigate what happens during those 2 hours.
Yeah.
They just accept it as a fixed variable.
But I have to push back on that logic for a second. Let's play devil's advocate. Let's say I'm a factory owner.
Okay.
I just wrote a check for $5 million for a state-of-the-art piece of industrial equipment from, Siemens or Toyota. Shouldn't the manufacturer's spec sheet dictate exactly how long it takes to switch gears?
You'd think so, yeah.
Right. Surely those elite engineers factored in the physical reality of changing a part. Isn't the downtime a hard-coded engineering fact?
And see, that is highly logical, which is exactly why the trap is so incredibly dangerous. It feels like a mechanical fact.
But it's not.
It's not. Here is where the illusion breaks down. The mechanical reality, the unavoidable physical swap, where the machine absolutely must be disabled and powered down, that might only take 10 minutes.
Just 10 minutes out of the 2 hours.
Exactly. The manufacturer's spec sheet might even say the internal mechanisms can be swapped in 10 minutes. The massive loss of time isn't occurring inside the machine.
Where is it happening then?
The loss is occurring inside the waiting pattern around the machine.
The waiting pattern around the machine. Wow, okay. That completely flips the perspective.
It really does.
So if the machine only needs 10 minutes to physically change its internal parts, where on earth are the other hour and 50 minutes going? Walk us through, like, the chronological reality of a typical line stop in a factory that's stuck in this blind spot.
Okay, picture the factory floor. The current production run of, say, blue plastic bottles finishes.
Okay, blue bottles are done.
Right. The operator hits the red button. The massive injection molding machine grinds to a halt. It goes totally silent. And only at that exact second does the setup process for the new red plastic bottles begin.
Oh, I see. So the clock is ticking, the multi-million-dollar asset is completely dead, and only then does the scramble start.
Exactly. First, the operator has to walk away from the machine to search for the right tools. They spend 10 minutes looking for a specific wrench, right, because the maintenance team borrowed it yesterday.
Classic.
Then they walk to the storage cage on the literal other side of the building to fetch the new mold. They bring it back, only to realize the machine surfaces have residue from the blue bottles.
So they have to clean it.
Right, so now they have to go find cleaning supplies. They clean the machine, then they spend 20 minutes unbolting the old mold. They put the new mold in. Then they have to find the manual to check the new temperature calibration settings.
It's just a constant scavenger hunt.
It is. And it gets worse. They run a test bottle. It looks okay, but company policy says they have to wait another 20 minutes for the official quality inspection team to wander over from Zone 4 to sign off on it.
And while this entire tragicomedy of walking, searching, cleaning, and waiting is playing out, that asset is producing absolutely nothing.
Nothing at all. Prasad uses this incredible, dryly funny phrase in the sources here.
Oh yeah, the intern quote.
Yes, he points out that during this entire scavenger hunt, the machine stands there like, quote, the most expensive intern in the plant.
It's such a devastatingly accurate description. You have a highly capable, incredibly expensive asset, totally immobilized, just standing there waiting for someone to hand it instructions.
And materials, yeah. And if we dig into the root cause of this, we realize this isn't malicious, right?
No one is trying to waste time.
Exactly. Nobody walked into work that morning plotting to waste 2 hours of production capacity. The system simply allowed too much work to happen after the stop.
Because no one ever bothered to write a script for it. If you don't explicitly mandate what happens before the machine goes quiet versus what happens during the silence, I mean, human nature dictates that we just do everything sequentially.
Right. One thing finishes, the next thing starts.
Yeah.
Without a standard classification system, sequential processing is just the default human behavior.
So if the machine itself isn't the problem, the process around the machine needs a rigid architecture.
Yes. Which brings us to the core methodology our sources highlight today. It's a concept originally codified by Shigeo Shingo at Toyota.
And it's known as SMED, right? SMED.
Right, SMED, single minute exchange of die.
Just to ground that term for you listening, a die in manufacturing is essentially a massive, highly customized tool used to cut or shape material.
Right, like a giant cookie cutter.
Exactly. Think of a giant 5-ton block of steel that comes down and stamps a flat sheet of metal into the shape of a car door. When you want to stop making left doors and start making right doors, you have to physically exchange that massive die.
And single minute in this context doesn't literally mean 60 seconds.
I mean single digits, right?
Exactly, under 10 minutes. The goal of SMED is to reduce these equipment setups and changeovers from multiple hours down to single digits. And the absolute genius of Shingo's methodology is that it achieves this without demanding massive capital investment in new equipment.
Which is huge.
It relies entirely on one incredibly crucial distinction.
This is the linchpin of the whole deep dive, the concept that completely changes how you view a process, the SMED split.
The split forces an organization to categorize every single action surrounding a changeover into one of two buckets: internal work or external work.
Let's define those really clearly.
Okay, so internal work consists of tasks that absolutely, by the laws of physics or safety, require the machine to be stopped.
Like physically unbolting that 5-ton steel die from the center of a hydraulic press.
Right. The press cannot be running while you do that. That is internal work.
Because nobody wants to lose an arm. Physics first, safety first.
Exactly. But then you have the other bucket, external work. These are tasks that can happen while the machine is still actively running the previous batch.
So what falls into that bucket?
Things like retrieving the tools, checking the new blueprints, staging the materials on a cart right next to the machine, pre-cleaning the new components, all of that.
Let me bring this down to a totally everyday level for you, the listener, just so you can really feel how absurd it is when we get this wrong.
I love everyday analogies for this.
Think about cooking a really complex dinner in your own kitchen. Imagine you're making this massive pasta dish.
Okay, I'm hungry already.
Right. But if you wait until the giant pot of water is at a rolling boil on the stove before you even open your refrigerator to start looking for your vegetables, and then you spend 10 minutes slowly chopping onions, you have just turned external work into internal work.
You force the stove to wait for you.
Exactly. That boiling water is your expensive intern just evaporating away, wasting energy while you look for a cutting board.
That is a perfect translation. The structural leak in any system begins the exact second. External work is treated like internal work.
It's so simple, but so destructive.
It is. If we map your pasta analogy back to a business-to-business manufacturing reality, the consequences are incredibly expensive. A wrench that could have been staged on a table an hour earlier.
Right.
When an operator has to go look for it while the machine is off, that wrench physically becomes downtime.
It stops being a tool and starts being a delay.
Yes, a calibration document that could have been reviewed yesterday. It becomes downtime.
There is a quote from the sources that hits this perfectly. When a necessary holding fixture is missing while the machine is stopped, it ceases to be a simple missing tool. It becomes, quote, a planning problem wearing safety shoes.
I love that quote. It highlights how a failure in process design basically masquerades as a physical real-time crisis on the factory floor.
You think you have a tool problem, but you actually have a staging problem.
Precisely.
Here's where it gets really interesting, though. And this is the central focus we really need to unpack today. If we're forcing the stove to wait, or forcing the stamping press to wait, why does it matter so much?
Right, if the machine is already paid for.
Exactly. The machine is paid for, it's just sitting there for 2 hours. Who cares?
Well, this is where we transition from looking at a stopwatch to looking at a balance sheet. The catastrophic hidden costs of ignoring this internal versus external task separation.
The financial domino effect?
Yes. The financial domino effect of a long changeover is profound, and honestly, it's entirely counterintuitive.
How so?
Well, if an operations manager believes the machine takes 2 hours to change over, they're going to do absolutely everything in their human power to avoid changing it over.
Because every time you hit that red button, you lose 2 hours of production time. So the incentive is just to never hit the button.
Exactly. So to quote-unquote justify that massive block of downtime, the plant is pushed toward running larger and larger batch sizes.
Oh, I see.
Instead of making 100 units of product A and then quickly switching to product B to meet customer demand, they will run 10,000 units of product A just so they do not have to endure the changeover penalty.
And on the surface, to an untrained eye walking the floor, that looks highly efficient, doesn't it?
It looks amazing. The machine is loud, it's humming along, making thousands of parts. The utilization metrics on the supervisor's spreadsheet are glowing green.
But it's a trap.
It's a massive trap. It looks brilliant until you look at the whole system. Because producing in massive unjustified batches immediately inflates your WIP, your work in progress.
Let's really break down what high WIP actually means for a company, because it's so easy to hear an acronym like WIP and just let your eyes glaze over.
Right. WIP sounds like a good thing.
We hear work in progress and think, oh, it means people are getting things done. But in this context, WIP is basically poison to agility.
Let's use an analogy for this too. Having high WIP in a factory is like buying a month's worth of groceries every single day because you're terrified of the 20-minute drive to the grocery store.
Oh, wow. That's a great way to put it.
Right. So your refrigerator is completely overflowing, your pantry is packed, your cash is totally depleted. And if you suddenly decide you want tacos instead of chicken tonight, you cannot pivot.
Because you're trapped by the massive pile of chicken already sitting on your counter.
Exactly.
That is exactly it. High WIP means you have massive wooden pallets of half-finished or, honestly, soon-to-be obsolete goods sitting all over your factory floor.
Just taking up space.
Right, and first of all, that ties up physical space, and industrial square footage is incredibly expensive.
Very expensive.
Second, it ties up planning attention. Some poor manager has to track where all these thousands of parts are in the building.
Yes.
And third, it destroys your response time. If your biggest client calls and needs an urgent custom order, you have to tell them no because you're in the middle of a 3-day run of a massive batch just to avoid a changeover.
It makes the whole business rigid. But the most painful part of that grocery analogy is the cash.
The cash flow. Let's talk about the cash flow.
Every single one of those half-finished metal parts sitting in a bin represents frozen capital.
Frozen capital.
Yes. It is money the company has already spent on raw steel, on electricity, on labor. But they cannot collect a single dime of revenue on it until it is a finished product sold to a customer.
So they've literally turned their liquid operating cash into a physical roadblock on their own floor.
Exactly. The plant looks incredibly busy. The forklifts are buzzing around, moving these massive pallets. People are sweating. The machines are loud. But the system has actually become entirely rigid.
This is the core tragedy of this deep dive. Hidden changeover inertia quietly mutates into catastrophic inventory bloat.
And this raises a really fascinating behavioral question.
What's that?
Well, if the system is this broken, if it's bleeding cash into frozen inventory, and if these changeovers are directly stripping valuable capacity away, why isn't corporate leadership panicking?
Seriously, if my bank account was tied up in thousands of half-finished plastic bottles sitting in a hallway, I would not be sleeping.
Right. You'd think executives would be having emergency board meetings about this every single day.
Why are they blind to it?
Because the truth is buried in the metrics.
Buried in the metrics. How?
The lost output and the tied-up capital are almost rarely quantified as a failure of setup. You won't see a line item on an income statement that says, money burned because Dave couldn't find a wrench.
Right. The accounting software doesn't have a code for Dave's wrench.
Exactly. Instead, these losses are smoothed over and buried inside aggregate efficiency metrics. The 2-hour downtime just becomes accepted as the baseline cost of doing business. It becomes an embedded production planning norm.
So the leadership team doesn't even see it as a problem to be solved. They just look at the dashboard and think, well, manufacturing is just a slow, expensive process.
It's actually far more insidious than that, unfortunately.
Oh, no.
Because they're running these huge batches to avoid the changeovers, their lead times stretch out into weeks or months. Customers are waiting longer. The warehouse is full. So the company starts to falsely believe they have a capacity problem.
Wait, a capacity problem?
Yes. The executives look at the data and say, we are maxed out. We need to make more parts faster to keep up with demand.
Oh, man. This is where the blind spot gets incredibly expensive, doesn't it?
It leads to what the sources wryly refer to as the heroic CapEx deck.
CapEx meaning capital expenditure.
Right. A team of directors will spend 6 weeks building this massive, beautiful PowerPoint presentation to justify asking the board for $10 million.
To buy a brand new, faster machine.
To increase capacity.
When in reality, they do not lack capacity at all. They just lack task separation.
Yeah.
They are spending $10 million to buy a new machine when they could have just bought like a $10 pegboard and a workbench to stage their tools next to the old machine.
It is a profound misallocation of capital, all stemming from ignoring the difference between internal and external work. They try to buy their way out of a behavioral problem using heavy machinery.
It's wild. So if the system is bleeding cash and management is completely disconnected from the root cause, what's the natural human instinct? Exactly. The operations manager walks out onto the floor, looks at the bottleneck, and starts pointing fingers at the people running the machines. Why is this taking 2 hours? Why are you guys moving so slow?
But our sources are crystal clear on this point. This is a structural failure, not a human one.
If you're listening to this and you manage a team, this is crucial for you. You have to validate the invisible labor happening on your front lines.
Yes.
This is definitively not an operator failure. In fact, if you look closely at these broken systems, the operators are usually the only reason the system is running at all.
That's entirely true. Because the company hasn't designed a standardized sequence, the operators are carrying the real functional setup process entirely in their heads.
It's like they're running a black market of efficiency down there.
That's a great way to put it.
They're smuggling actual productivity into a broken corporate system using completely unapproved workarounds. Walk us through what the operators actually know that the official corporate standard operating procedure manual doesn't.
Well, the standard operating procedure manual is usually a pristine white binder sitting on a supervisor's desk that hasn't been opened since, 2019?
Right. It's totally theoretical.
Yes. But the operator on the floor knows the actual physical reality. They know that the torque wrench specified in the manual is always missing because the night shift maintenance guys borrow it.
Right.
They know that the hydraulic clamp on the left side of the die is slow and jams if you don't hit it at just the right angle with a rubber mallet.
Things no manual would ever say.
Never. And they know that if they wait for the official quality inspector in Zone 4, like the manual says, it's going to take an hour. So they have to go find Dave in Zone 2, who will sign off in 5 minutes.
Shout out to Dave in Zone 2, keeping the economy running.
Exactly. So the knowledge of how to change the machine over is highly present. The people are smart, they're resourceful. The problem is that the sequence is not documented or supported by the environment.
Without a designed, enforced script, you just have incredible variability.
Right, because the operators are relying purely on tacit knowledge.
So one operator might have a personal habit of prepping their tools early, and their changeover takes 40 minutes.
And another operator might do things strictly sequentially, waiting for the machine to stop before they go looking for Dave in Zone 2, and their changeover takes 2 hours.
And this brings us to a really fascinating tension in how companies try to improve. We talked about the heroic CapEx deck, right? The $10 million machine.
Yes.
The sources point out that empirical experience shows human elements like preparation, staging, and organization are typically much faster and vastly less expensive to improve than technical engineering elements.
It is a massive asymmetry in business logic. Upgrading the mechanical engineering of a machine to shave off 10 minutes of internal time that might cost hundreds of thousands of dollars, require external consultants, and take 6 months to install.
Right.
Upgrading the organization of the tools around the machine to shave off an hour of external time. That costs $50 for a shadow board and takes 1 afternoon.
It's totally absurd when you frame it that way.
It is.
But it makes sense psychologically. We would rather build a committee of 12 highly paid directors, put them in a conference room for 6 weeks to discover the concept of a stopwatch, and then sign off on a shiny new machine, rather than just asking Dave to stage the tools an hour earlier.
We are addicted to complex, expensive solutions for simple behavioral problems. We constantly conflate financial effort with operational effectiveness.
Wow, say that again. Conflate financial effort.
With operational effectiveness, the CapEx deck feels like a massive strategic win. The executive gets to stand in front of the board and point to a $10 million investment in the future.
Right.
Stating a wrench on a table feels mundane. It doesn't get you a promotion, but the mundane solution is the one that actually recovers the hidden capacity.
Okay, so let's get into the mechanics of the solution.
Let's do it.
So if we're bleeding cash into frozen inventory, and leadership is ready to sign a $10 million check for a new machine out of sheer ignorance, how does an operations manager actually break this cycle without asking for a budget?
Well, the sources provide a highly specific, multi-day SMED diagnostic playbook. And the best part, for anyone listening who wants to try this, it can be run in under a week.
Under a week. That's incredible. But you can't just run out onto the factory floor on Monday morning yelling about task separation and waving your arms.
No. You have to set the stage. First, you ensure your decisions are driven by real data, typically by tracking OEE.
OEE, overall equipment effectiveness. For those who aren't living in manufacturing dashboards every day, this is basically the gold standard metric.
Right.
It measures availability, performance, and quality. An OEE of 1.0 or 100% means you are manufacturing only good parts as fast as possible with no stop time whatsoever, which is basically impossible.
Right. World-class manufacturing plants usually hover around an OEE of maybe 0.85, meaning 85% of the theoretical maximum capacity is actually being realized.
Okay.
But to fix your changeovers, you need to look specifically at the downtime reason codes within that OEE data. You need to know exactly why the machine stopped and for how long.
So once you have the data, you have to pick a pilot area. You don't try to fix the whole factory at once.
Never.
You find a bottleneck machine, the one that is holding up the rest of the plant that has long, highly variable changeover times.
And crucially, the sources say you must select an area where the employees are engaged and motivated to make things better. You want a quick win with a willing team.
So you have your team, you have your bottleneck machine. Day one of the playbook is pure observation.
Yes, you're going to record one full changeover end to end. And you don't need a film crew. A smartphone video propped up on a tripod is perfectly sufficient.
Just a phone?
Just a phone. The goal is to capture the baseline, gritty reality. And the psychology here is critical. The mantra is no theater, no blame, just time.
I love that. No theater, no blame, just time. Because if you think about it from the operator's perspective, if a manager walks out with a stopwatch and a camera, their immediate thought is, they're timing me to see if they can cut my job.
Exactly. Or they want me to work twice as fast.
Right, so you have to explicitly tell the operators, we aren't timing human speed, we are timing the process to see where the system is making you wait.
That distinction is everything. If you don't disarm that fear, the operators will put on what we call industrial theater.
Industrial theater.
Yeah, they will suddenly work at this frantic, unsustainable pace while the camera is rolling, which totally ruins your baseline data.
You want them to do it exactly as poorly as they usually do it.
Yes. Once you have the video, the team maps every single element. Many practitioners use sticky notes on a massive wall, creating this visual timeline of every single action taken from the moment the last good part of the old batch is made to the moment the first good part of the new batch passes inspection.
So you have this giant wall of sticky notes mapping out a 2-hour ordeal.
Yeah.
Day 2 is what the playbook calls the great split.
This is where the analytical heavy lifting really happens. The team takes that giant wall of sticky notes and they interrogate every single step.
They ask, is this action internal?
Right. Meaning, did the massive stamping press absolutely have to be powered down and locked out to do this?
Or is this action external? Could we theoretically have performed this action while the press was still stamping out the last batch of parts?
And this must be where the light bulbs start going off for the team.
Oh, yeah.
Because they're looking at the wall and they realize that half the sticky notes currently happening while the machine is dead, searching for the manual, fetching the clamps, mixing the cleaning solution, are actually external tasks.
It's usually a very confronting moment for management, I bet.
Highly confronting.
Yeah.
Because they realize how much capacity they have just been throwing away for years.
Yeah.
Which leads directly into days 3 and 4, resequencing and converting.
The first action in resequencing seems incredibly simple, but it's profound. You physically move all the sticky notes representing external work to a phase before the planned stop time.
You're building a new script. In the new reality, the operator gathers the wrench, pre-mixes the cleaning solution, pre-stages the new steel die on a heavy-duty cart right next to the machine, and has Dave, from Quality Review, the calibration checklist. All while the machine is still happily humming along, producing the last 50 parts of the previous order.
Just doing that, just moving the external sticky notes to the left side of the timeline, often cuts the changeover time in half.
At least in half, yeah.
But the sources go deeper into what they call conversion tactics. And this is where we transition from process organization to actual engineering. How do you look at a truly internal task and engineer a way to convert it into an external task?
Let's look at the physical mechanics of this because it gets brilliant. One of the primary tactics is advanced preparation of operating conditions.
Give us an example of that.
Okay, let's say a machine requires a massive steel die to be heated to 300 degrees before it can safely stamp metal without shattering. Historically, the operator would unbolt the old die, put the cold new die into the machine, and then the machine sits completely idle for an hour while internal heating elements slowly bring the steel up to 300 degrees.
That's an hour of internal downtime.
Yeah.
And you can't safely stamp the metal when it's cold. Physics demands the heat. So how do you convert that?
You take the heating process outside the machine. You invest in a separate, relatively inexpensive external heating jacket or preheating cart. The operator places the new die on this cart and brings it up to 300 degrees 2 hours before the changeover even begins.
Wow.
When the machine stops, you swap out the old die, swap in the preheated die, and the machine is immediately ready to cycle. You just converted an hour of internal downtime into an hour of external preparation.
That is exactly like preheating your oven while you're still chopping vegetables instead of putting a cold casserole into a cold oven and waiting.
That's a perfect parallel.
Brilliant. What else do they use for conversion?
Duplicate jigs are a huge factor.
A jig, for context for the listener, is a custom frame or plate that holds a raw part exactly in place so the machine can work on it.
Right. Often, a massive amount of internal time is wasted just calibrating and aligning the raw material once the jig is inside the machine. The operator's in there with calipers, tapping it with a mallet, trying to get it perfectly straight while the machine is dead.
So how do we convert the alignment process?
By using duplicate jigs, the company buys a second identical jig. While the machine is running the current batch on jig A, the operator is at a workbench externally, placing the new raw materials into jig B. They're measuring them, aligning them perfectly, and locking them down.
So it's all ready to go.
Exactly. When the machine stops, you pull jig A out, slide the pre-aligned jig B in, and you are ready to go. You just move the entire alignment process from internal to external.
It's literally the NASCAR pit crew pre-mounting the rubber tire to the metal rim before the car even arrives in the pit box.
Yes.
If they waited until the car stopped to try and stretch the rubber over the rim, the pit stop would take 20 minutes.
Yeah. Exactly right. And there is one more engineering conversion tactic that is absolutely critical, and it has to do with how things are fastened. Eliminating bolts.
Bolts seem pretty standard, though. What's wrong with a bolt?
Unthreading and rethreading bolts takes a massive amount of human time and physical effort. Think about an operator having to use a wrench to unscrew 8 massive long-threaded bolts to remove a heavy plate.
Right.
And then screw 8 new ones back in. It might take 15 minutes of solid internal downtime. The SMED conversion tactic is to eliminate threads entirely wherever safety allows.
What do you replace them with?
You replace the bolts with quick-release mechanical clamps, quarter-turn fasteners, or pneumatic locks. You push a button, air pressure releases the clamp, and the plate slides out. You turn a 15-minute wrenching task into a 5-second internal task.
Okay, so let's summarize where we are in the playbook. By the end of day 4, the team has a completely new script. They have moved all the external work to the front. They have engineered away the bolts. They are preheating the dies. They have duplicate jigs. They have taken a 2-hour ordeal and mapped out a 15-minute sprint.
It's a total transformation.
What happens on days 5, 6, and 7?
This is where the rubber meets the road. You train, enforce, and streamline. You brief the operators on the new sequence. You make sure the external staging area is clearly marked. And then you run 2 or 3 actual changeovers using the new script. You log the times against your new 15-minute target.
And let's be real, it won't be perfect the first time. The operators have muscle memory from doing it the old slow way for 5 years.
Muscle memory is a huge source of resistance. They will automatically reach for a tool that isn't there, or they'll forget to preheat a component because their brain is just wired to do it sequentially.
Right.
That's why the final days are about reviewing the variances. You look at the video of a new changeover and say, okay, why did it take 25 minutes instead of 15? Where did the process drift from the script?
You keep what works and you fix what drifts. Maybe the quick release clamp is sticking, so you adjust it. Maybe the external staging card needs better wheels.
You refine it until it is stable. And once it is stable, you lock that in as the new standard operating procedure. And the payoff for this 1 week of highly focused effort where we haven't spent millions of dollars, we haven't bought a new machine, we have primarily just reorganized human time and bought a few clamps is massive.
I mean, the sources show case studies with 10 to 50% reductions in changeover time across the board.
It's incredible.
There is a specific study in the sources on flexographic printing. For anyone unfamiliar, flexographic printing involved these massive high-speed rotary presses that print graphics onto continuous rolls of plastic or paper.
Right. Think of the labels on your soda bottles or the plastic packaging for your snack.
Exactly. They are incredibly complex to set up because you have to align different colors of ink perfectly.
Very complex. In that case study, they applied this exact SMED playbook. They moved the ink preparation and the cylinder staging to external time. They cut the changeover time down to just 29 minutes.
Wow.
And because they were doing multiple changeovers a day, that single week of reorganization achieved a roughly 10% overall productivity improvement for the entire massive line.
pushing their OEE up to nearly 0.89, which is just world-class territory.
All done simply by reusing human time and machine availability more intelligently.
It is the ultimate proof that capacity is often hidden in plain sight, trapped beneath bad sequences and lazy assumptions.
Absolutely. So if we zoom out from the factory floor for a minute, what is the journey we've just taken?
Well, we started by believing that a machine or any complex system, whether it's a factory or a software deployment pipeline, dictates our time. We treated a 2-hour delay as an immutable law of physics.
But then we realized the machine isn't the culprit. The waiting pattern around it is.
The machine only needs 10 minutes.
Right. We saw how failing to separate internal and external tasks, waiting for the machine to stop before we start looking for our tools, creates a devastating financial domino effect.
It forces managers into running larger batch sizes, which bloats the inventory, freezes the operating cash in massive piles of half-finished goods, and tricks leadership into buying $10 million machines they do not actually need.
And finally, we learned the zero-cost, one-week SMED playbook to reclaim all that lost capacity. We observe without blame, we split the tasks, we move the external work out of the stoppage window, and we convert internal friction into external preparation.
So powerful.
If there is a single ultimate field principle for you to take away from all of this data today, a golden rule you can apply to any system, it is this. If the machine does not need to be stopped for the task does not belong inside the stoppage window.
That one sentence, if rigorously applied by a team, that can recover more organizational capacity than a dozen multi-million-dollar transformation meetings.
Jesus.
It is such a powerful lens to look through, and I want to leave you, our listener, with a final provocative thought to chew on. You probably do not operate a massive flexographic printing press.
Probably not.
But look at your own workday tomorrow. Look at your own personal changeovers. Switching from deep, focused work like writing or coding to a barrage of Zoom meetings.
Yeah.
Or finishing one massive project and trying to pivot your brain to start another.
That transition time is huge.
It is. How much of your own personal internal downtime, the time where you feel totally stuck, exhausted, and unproductive at your desk, is actually just external work that you forgot to stage?
Oh, that's a great point.
Are you waiting until the Zoom meeting starts to go looking for the document you need to present? Are you letting your own mental engine completely cool down while you go searching for a metaphorical wrench in your inbox?
You're forcing your own internal stove to wait.
Exactly. Think about how you can separate your own internal and external tasks. Stage your tools before you need them. Preheat your dies, mentally speaking. Do not let your own capacity become the most expensive intern in the plant.
Love that.
Thank you so much for diving deep with us today. It has been an absolute pleasure unpacking these hidden mechanics with you. We will catch you on the next deep dive.